Here we're going to formalize and prove the fundamental theorem of calculus, the one part of it. We'll call this the function form. We just saw a few videos on this and with particular examples, but we're going to prove it in general. Now this is a very interesting idea because what it's doing is it's connecting these two ideas, because remember, the integral, we saw the integral and we defined the definite integral to be in terms of area, right? Finding the area under curves. So here I'm making a connection between finding areas under curves and the derivative. So what the fundamental theorem here says is it says that every continuous function, lowercase f, which by the way I'm gonna notate. Sometimes it's hard to distinguish between uppercase and lowercase f. Often when you've got two functions related by a derivative, you'll use uppercase and lowercase letters to distinguish them, at least in these type of functions here. So I'll just put tail. I'm going to make all my lowercase f's with blue in blue, but I'm also going to put tails on them. But it says that every continuous function, in this case lowercase f, has an antiderivative, and namely capital F. And it also says that integration, which is just where we can see indicated by the integral sign, and differentiation, taking the derivative, those are inverse operations. So some really powerful ideas here connecting derivatives, antiderivatives, and areas, which is just, it's really profound, and it's again, as I keep emphasizing this, it's not obvious. So let's talk about the proof here. So we're trying to show that the derivative of capital F of x, notice capital F of x is an integral function. I'm gonna use that language. It's a function defined as an integral, and it's defined to be the area you get when you accumulate area under lowercase f from a to x. Its derivative is lowercase f. So we're going to do this problem by just reminding ourselves what the definition of the derivative is, right? The definition of the derivative would be the limit as h goes to 0, f of x plus h minus f of x divided by h. So connecting this to my diagram here, notice that capital F of x is this area accumulating function defined as an integral. That's this here, right? There's really no other way to indicate capital F of x in this picture except to point to that region of area there. That's capital F of x. It's the function that's accumulated area from a to x. So to find its derivative, since it's an area accumulating function, we basically are trying to figure out what is the instantaneous rate of change of area it's accumulating right at this moment, right at x. So how do we do that? Well, we're going to go over a distance h, as usual. So now that's x plus h, and this distance is h. And we're going to find the area. We're going to find the area of this black region here. And we're going to let h go to 0, and once we do that, we'll have an expression, hopefully, for the, well, what we'll have is lowercase f of x, but this idea of making h go to 0, it's going to kind of squeeze that thick region into a really thin one, until it's infinitely thin, and then we'll see that the actual rate of change of the accumulation of area is f of x, lowercase f of x. So let's do some replacing here. So capital F of x plus h, well, if you just plug that into your in for x, that's going to be the integral from a to x plus h. So it's a to x plus h under f of x, but the lowercase f, I need to write this as f of t, dt, minus capital F of x is just the integral a to x under f of t dt divided by h. And now, if you look carefully at those integrals, this one on the left here is basically telling me to accumulate area from a all the way to x plus h, and then I'm going to subtract the integral from a to x, which is this. And so if you think about it, that just leaves, by property of integrals, that just leaves this. That just leaves that region, which is the integral from x to x plus h. So I can write this as the limit as h goes to 0 of one integral, the one from x to x plus h, underneath f of t dt. And now here's where that mean value theorem we talked about earlier comes into play. I've got an expression for this integral here. It's underneath a curve that's changing in a smooth way. But what the mean value theorem says is that there is some place here, some c value, I'm going to call it like a c sub k. There's some c sub k here that will allow me to create a rectangle whose area is precisely the area under this curve right here. So again, I'm basically saying that I can now rewrite this integral here as just an expression for an area of a rectangle whose width is h and whose height is f of ck. So this integral here is just base h times the height, which I need to use that in blue to be consistent, f of c sub k. Right, that's the height of that rectangle. It has the exact area as the black region by the mean value theorem. So h times f of c sub k divided by h. And now you see those h's cancel. And so now what am I saying? I've eliminated the problem of dividing by 0. F of c sub k, as h goes to 0, what you do is you're squeezing, you're making those rectangles that I'm creating, and it's a dynamic situation because as h goes to 0, that c sub k is going to change, right, depending on where you are, but it's going to be constantly creating rectangles whose area is equal to the actual value of the integral. But as h goes to 0, c sub k goes to x. It gets kind of squished in between x plus h and x, so it gets squished and pushed towards x until it becomes f of x. So this becomes lowercase f of x. Alright, so there's the proof. It's I think this is hard for students to understand at first, and the reason I think it's hard is because the entire first part of your calculus experience, you've been told that derivatives relate to slopes to tangent lines, here I'm talking about the derivative of a function, and I'm not talking about slopes of tangent lines. I'm talking about instantaneous rates of accumulation of area, because capital F is a function that's accumulating area. And so its derivative should be the instantaneous accumulation of area at a given instant. Nevertheless, I think it's a difficult proof to get on a first go, so it's worth looking at a few other times. But in any case, what you'll really want to make sure you understand is how to apply it, and that's where the next video will come in. So again, here's the proof of the first part of the fundamental theorem, and we'll look at some of the applications of this in the next video.